Hello, good morning. Um, this is going to be the second cycle of our lecture. The first lecture provided a concise introduction to basic statistics. We treated concepts like the mean, median, mode, weighted averages, measures, basically measures of central tendency. And then I also tried to highlight the importance of measures of dispersion in data uh, analysis. So today we're going to be focusing on probability and level of significance and the formulation of valid hypothesis and hypothesis testing. All right. I think including student t-test and one-way analysis of variance as well. All right. So the t-test and Anova. I'm sure you've heard of t-tests before. So what is t-test and Anova? We're going to get the basics. What is a null hypothesis and what is the alternative hypothesis? The null hypothesis is presented as this is H naught. H1 is the alternative hypothesis. And why is statistical significance represented as a p-value as equal to 0.05? We're going to talk about that today. And this little figure here is just for, for your view. You can read more about it if you want. Z-score, probability density. You use this kind of statistics when you're dealing with a population. Those people that do public health research, epidemiology, field research, and so on. Yeah. All right. So a hypothesis is a prediction that you have about a specific group. Okay, that's what a hypothesis is. A prediction you have about a specific group. So the alternative hypothesis is the experimental hypothesis, also called the experimental hypothesis. A significant difference tells you if there's a significant difference between, let's say, two groups, right? Between samples. While the null hypothesis assumes or asserts that there is no difference between two samples, two populations, two groups, and so on. You understand? So it makes it very easy. The null, of course, the English word null means no, nothing, no difference, right? Okay, so to get a statistically significant result, you need to show that your experimental group falls on a higher end of the probability. So we have the one-sided test and the two-sided test. So I won't bother reading this. You have the lecture notes or you can read this on your own, from the slide. Let me just show you what we mean here from this figure, right? So you look at this figure of statistical, it talks about statistical significance. You have three portions of the figure. You have this unlikely observation on the left-hand side. You have unlikely observation on the right-hand side, which bridges along the 95% statistical significance threshold. It's supposed to be present here too, but we just, trying to show the one-sided test here. So this is where your p-value definition comes from. If you have 95% significance threshold, the remaining 5% is here. So 5%, that's 1 over 20. It means there's a 1 chance. There's a, out of 20 chances, out of 20 probabilities, there's a 1 chance that your reading is significantly different. Something like that. I'm trying to make sense of it, but you get it when we go forward, yeah? So the probability that observed result is true. The level of significance is 0.05, of course, 5%, right? This is the 95% confidence threshold. this is where you expect your more likely observations. Or when there's a 5% chance that your observation is significantly different from one group to another, then statistically that's significant. So this is for one-sided tests. For two-sided tests, you have this same coloration here. So basically that's what it means. So I'm sure if you read this now and you correlate it with this figure, it will make sense. 95% certain our experimental effect is genuine, of course. Okay, so the p-values, the probability that the observed result was obtained by chance, and it stands for power. Of course, the p stands for power. And this is the definition of a p-value. The power of a statistical hypothesis tests. A hypothesis test measures the test ability to reject the null hypothesis. Of course, the null hypothesis assumes that there's no significant difference. Now, the p-value, the power of the p-value is to prove that there's a significant difference. And if the p-value is less than 0.05, it means that if it's less than 0.05, that's your 5% chance. If it's less than that, then we are saying that your null hypothesis is false. We are saying that there's a significant difference. But if your p-value is greater than 0.05, it's greater than 5%, then we have to reject we have to accept the null hypothesis. Means yes, there's no significant difference. Basically, that's what we are saying here. The alpha level is set a priori. That's the p-value, usually 0.05. With this p-value, we can be 95% certain that our experimental effect is genuine. If your p-value is less than result, is your p less result is, if your p-value, right, is less than your alpha level set here, that's a 0.05. So you have to reject the null hypothesis, which assumes that there's no significant difference. If your p-value is less than 0.05, there's a significant difference. So you reject the null hypothesis and you accept the alternative hypothesis. Or if your p-value is higher than this 0.05, then you accept the null hypothesis and you reject the alternative hypothesis. I think that makes it clear. Yeah. So looking at this and then looking at that, right? Okay. This is where the statistics takes place. Yeah. All right. Okay. So now, of course, with everything, you should have to account for errors, right? So there's what we call the type 1 error, which is the false positive, and the type 2 error, which is the false negative. So now what's type 1 and type 2 errors, right? So type 1 error, false positive, is what we incorrectly accept the alternative or experimental hypothesis. When the null hypothesis is true, but we mistakenly reject it and we accept the alternative hypothesis, that's a type 1 error. Alpha level 0.05 means that there's a 5% risk that a type 1 error will be encountered, all right? So type 2 error, which is the false negative, you reject the alternative or experimental hypothesis when it should be accepted. So basically that's what we are saying. So for type 1 error, you reject the null hypothesis when it should be accepted. Type 2 error, you reject the alternative hypothesis when it should be accepted, basically. So scientists care more about accepting a false result than rejecting a true one. Okay. So power is equal to 1 minus probability of type 1 error. The maximum power a test can have is 1. The minimum is 0. Ideally, we want a test to have high power, close to 1. Of course, you can read more about this. This is basic statistics and mathematics, right? So here is an example of how these errors work. Let's say you start dating someone. Well, this will bring things into perspective, right? We're talking about dating. People want to hear stories like this. Okay. So imagine I say you just started dating someone. On the first date, he or she mentioned that her birthday was coming up this week. All right. or you can't remember the exact day. It might be today or maybe not. So since you can't remember the exact day, embarrassed to admit it, you decide to make a guess instead of asking how you decide to guess because you're embarrassed to admit that you can't remember the date. So you have two choices. When you see him or her today, you can say happy birthday or say nothing, hoping that today isn't her birthday. The reality behind the situation is pretty simple. Either today is her birthday or it isn't. So if you say happy birthday when it is not her birthday, it's like a type 1 error, right? You're saying happy birthday when there's no birthday. The null hypothesis, there's no significant difference, or you reject it. That's type 1 error. You understand? So you're saying happy birthday when there's no birthday. All right. If it's a false positive now, that's a false positive. That's type 1 error. I'm saying it is your birthday when in fact it isn't. Conversely, staying quiet when today is her birthday. What if today is her birthday and because you're not sure today is her birthday, you kept quiet? So instead of accepting that today is her birthday, you don't know. So you rejected that it was her birthday and you stayed quiet. That's type 2 error. It's a false negative. But today is my birthday and you said nothing to me. You missed it. All right. So I think I hope this makes sense. All right. Okay. Research question example. So let's pretend you came up with the following theory. Now we're going to venture into the t-test now and Anova. So having a baby increases brain volume associated with possible structural changes. So for a pregnant woman, when a woman gets pregnant and has a baby, her brain volume increases. This is a hypothesis. It can be right or wrong. We'll see. We'll have to prove it later. So this is just a picture. There is a map to show population, Z-test, t-tests. Z-test is usually used for population statistics. T-test is used for samples. I'm going to talk about t-test later, don't worry. Some problems with a population-based study, of course, is you have the costs. I think this part will be treated by the other lecturer, I'm sure. So, of course, with the population, you have to deal with cost, not able to include everyone, of course, too time-consuming, and then the ethical rights to privacy. So realistically, in most cases, of course, researchers can only do sample-based studies. If you're backed by huge grants and by some big government or a very strong body to oversee population research, why not? Okay. So t-test. Well, in t-test, you just want to see the differences between samples, two samples mostly. The t-test is for two samples. You compare and differentiate between sample means for two groups. Okay. And this is the mathematical representation of a t-test. You can find this out if you want. Mostly nowadays we use statistical softwares like SPSS and so on. All right. Of course, we have done the standard deviation before. It is key to interpreting statistics. The difference between two means, because the standard deviations between samples will come into play. Those are the units from which your variance emanates from, right? You need variance. Without variance, you can't have differences, right? It's variance that the variation that gives differences between two samples and two groups, right? So now this is what we're talking about, two sample t-tests, now pre and post. We have, before I come back here, we have three types of t-test. There's a one sample t-test where you're comparing the sample to a mean specific value. There's an independent sample t-test on the other hand, you're comparing two different groups. And then the paired sample t-test is the same person, same group, or you're comparing maybe at 2 time intervals, for example, just like this example. This is the lady before she gave birth. She wasn't pregnant here, right, on the left-hand side, and here after she gave birth. And our hypothesis was you would use two sample t-tests if you wanted to determine if two samples are different. So we'll look at our previous hypothesis. What was our previous hypothesis? Was having a baby increase your brain size, right? So then it means we'll have to get the data of this woman before she became pregnant and after she became pregnant and gave birth to a child, right? So this is the null hypothesis. The null hypothesis, of course, will assume that there's no significant difference between brain size before and after giving birth, while the alternative hypothesis will say the brain is significantly smaller or significantly larger after giving birth, right? Of course, if you remember that very well. Okay, so now looking at the data, before she delivered, look at her brain size. Of course, you need replicates. You can't just give us one reading and see that statistics. So you see replicates. Then 6 weeks after delivery, you take these readings again. Okay. All right. And these are the means. This is the mean. This is paired sample t-test. The same individual but different time intervals. This is the mean. This is the mean. 1,300 and 1,236, 1,271 points first. Now these are the differences. Okay. So this calculate the t-test, of course, using those examples, those calculations. We can do this statistically. Now, this is the p-value after calculation. You remember our p-value, the p-value is less than or equal to 0.05. There's a significant difference. The p-value is greater than 0.05. There's no significant difference, right? So here the p-value is 0.003, it's less than 0.05. So it means you accept the alternative hypothesis. You have to reject the null hypothesis here, right? And the p-value is this. It means 119 is significantly higher than 113, right? That's the conclusion here. So it means delivery, the brain is significantly enlarged, right, after giving birth. That's the hypothesis. Women have significantly larger brain after giving birth, right? So this is just an example of t-test. So these are the types of t-tests. Of course, I've mentioned them. One sample versus hypothesized mean, independent groups, two separate groups t-test, and then the repeated measures, the paired sample t-test, the one we just did, right? Okay, then Anova, it's the t-test, but for 3 samples or more. Literally, that's what Anova is. Analysis of variance, right? We're comparing 3 or more samples. Basically, that's it. And I think I can leave this with you to read. I don't need to say much. This will be better demonstrated if I can do some of this statistics on SPSS, maybe in a video or something. Okay. So what can be concluded from ANOVA is there's a significant difference somewhere between groups, of course, not where the difference lies. Of course, finding exactly where the difference lies requires further statistical analysis called post-hoc analysis. Of course, yes. So maybe you have to find time to do that. If I have the time, I'll do a video demonstrating this on SPSS. You can read more about this, right? So conclusions from this slide, the Z-test for populations, Z-test is mainly, in most cases, used for population statistics, T-test for samples, ANOVA, compare more than 2 groups in more complicated scenarios. Okay? So please, if you have any question, you can drop your questions in the comment section, and please like and subscribe to the channel. Thank you very much. I think this makes things easier instead of fixing classes and not having the opportunity to run this. Thank you.